All right, guys, welcome. We are going to be working on a couple of lessons today, actually, in our continued discussion of OSPF. I was going to do one lesson today, and I thought, you know what? These lessons are very similar to each other, and in the interest of maybe saving a little bit of time, we can kind of combine the lesson 34 and lesson 35 together. Specifically, what we're going to be covering today is OSPF media dependencies and network types, and then we're also going to be talking about the configuration of those network types as well. Now, actually, that would mean that we would have a 3.5-hour lesson, but because we're going to be combining these concepts together, I don't think it will quite take that long. Actually, I don't think it will take that long at all. And also, we've been talking about some of these concepts over the past last few lessons anyway. Certainly the last lesson we took a look at some of these concepts as well. So what we're going to do in the first part of this lesson is we're going to talk about specifically OSPF media dependencies. In other words, how does OSPF change when it's dealing with multi-access networks, with broadcast networks, with point-to-point networks, with point-to-multipoint networks and non-broadcast networks and so on. So we're going to talk about that. And then we're also going to spend some time talking about how that affects the overall state machine between OSPF peers. We'll take a revisit on the Drbdr election process. We're going to, of course, talk about the 6 different network types, how OSPF handles next hop processing when it's dealing with like a broadcast network versus a DR type of propagation of LSAs that are getting flooded throughout the area, as opposed to, say, a point-to-multipoint scenario where next hop processing is modified, or at least the next hop address is modified. We'll also take a look at some of the typical network type design issues that you would see with the different network types. And then based on those requirements, what network type should we be running in our topology, and so on, okay? OSPF network behavior is going to change depending on what type of media that network is being configured on. Whether it's Ethernet versus frame relay, PPP, frame relay point-to-point, frame relay point-to-multipoint, and so on. OSPF actually defines network types to deal with different media type characteristics in our topology. Hellos, updates, those types of things, are they going to be sent with multicast? Are they going to be sent with unicast? Who forms the adjacency? What is the adjacency process? What is the neighbor relationship process between these peers? How is the next hop going to be calculated? And we'll talk about this, and we'll see this in some of our configurations. For example, the next hop, it controls how we forward routing information, how we handle links between the different peers. All right, so let's start by talking about the 6 different network types that exist in OSPF. And I'm going to keep some notes here. And we'll kind of make some, take some notes as we go through the process so that you guys can reference this a little bit later on. 6 different network types in OSPF. All right. And the first network type is probably one of the more common ones, which is just simply a broadcast network type. All right. The second one is non-broadcast. And the third type is point-to-point. Come on, not point-to-point-to-point. All right, there we go. The next type is point-to-multipoint. And network type 5 is going to be actually kind of a special Cisco type. It's not actually defined in the RFC. We'll take a look at the RFC a little bit later on. That's going to be point-to-multipoint non-broadcast. All right, and then finally, a special case or a special use case network type, which is called a loopback. All right. So we're going to end up grouping these different network types together based on one specific element in each of these different network types that OSPF recognizes. and it's going to be based on LSA Type 2s. And we remember from our last discussion, Type 2 LSAs are network LSAs. Those network LSAs allow us to identify essentially multi-access networks and who's attached to those multi-access networks, who the DR is, who the BDR is, and so on. We did discuss that previously in our previous exercise. We're going to spend some more time talking about that today, and then we're going to take a look at some of the configurations as we and some debugs as we do some configurations. We're going to do some ad hoc topology design today because my stupid GNS3 is not loading my topologies for some reason. Okay. So LSA Type 2, those are going to be generated by the DR. And if you recall from our previous discussion, network LSAs are built to kind of simplify the calculation of the OSPF topology to cut down the number of adjacencies that we have to have, but this is only going to occur in multi-access networks. Okay? One of the things that we saw in our last exercise as well is that network types don't technically have to match for the routers to actually form an adjacency, but the network types themselves have to be compatible. And that may be something that you're going to run into on the CCIE lab or even in the written exam where they might have commingled or co-mixed or mixed network types between the peers, but that doesn't mean that you can't still form an adjacency. For example, it's entirely possible to establish a network type or an adjacency between a point-to-point interface and a broadcast interface. It is possible to establish adjacencies between point-to-multipoint and point-to-multipoint non-broadcast and so on. So that's really what we're going to do, and that's kind of the second half of this discussion here, is to kind of take a look at different configuration scenarios, and we'll build out our topology, and of course it'll be saved in the Google Drive for you guys. Okay. So like I said, network types don't typically have to match, but when you change the network type, or when OSPF discovers a different network type, it might change some of the attributes that are required for the routers to form an adjacency. So things like hello timers, dead timers, those are going to possibly be changed. Whether or not automatic neighbor discovery is going to be permitted or denied based on the type of network. We'll define whether or not you have to do static neighbor statements to define the neighbor statically. We'll see different scenarios, and we're going to kind of build on a topology that essentially allows us to see all these different network types in action and how they work together. So there are attributes that do have to match, even though network type is not technically one of those attributes that has to match. So what makes the network types compatible? In other words, even though they may not match, what allows those network types to work together? It actually has to do with the Type 2 LSAs. Specifically, are we going to use a Type 2 LSA, or are we going to not use a Type 2 LSA? So we group essentially our network types together as broadcast or non-broadcast or point-to-point, point-to-multipoint, and so on. Remember, the Type 2 LSAs are going to be generated by a DR or BDR, and that describes who is adjacent with the DR within that multi-access network. Those are not flooded outside the area that they're originated in, and really they're only specific to one scenario. All right? And that scenario is when we have a multi-access network. Okay? There are instances where a Drbdr election is either not supported, or it could cause problems in our overall implementation. An example would be like a DMVPN network environment where the network type might be conducive to establishing a Drbdr relationship, but we don't want our spoke routers in that particular scenario to necessarily become DRs of the topology, because the routers have to have a permanent full adjacency with all the spoke routers have to have a permanent full adjacency with the DR. We actually have a whole nother lesson. We still have to go back and do the EIGRP one as well with regards to how EIGRP adjacencies are hold on one second. Sorry about that. Where OSPF adjacencies are required and Drbdr elections are required, but we have to make sure that we maintain the right topology to ensure that those establishments are done correctly. We see a similar concept in EIGRP, not from the perspective of doing some sort of election with a DR or BDR, but for the purposes of being able to dynamically establish adjacencies using multicast as opposed to statically configuring our neighbors using unicast. Okay? So we know that we utilize the Drbdr election to optimize OSPF operations on a shared segment. It's going to allow us to reduce the number of adjacencies that we have in our topology. It also allows us to reduce the LSA flooding or LSA replication that's going to occur between the peers in that multi-access network, and most importantly, simplifies the OSPF calculation process. We only need to recurse once to the DR. We solve the spanning tree topology, the shortest path tree topology to the other nodes based on that single recursion to the information that we're getting from the DR. All right, so the network types that actually use a type 2 LSA are broadcast and non-broadcast. So let me make a note of that. Uses a LSA type 2, which is a network LSA, which means there is a Drbdr election in this process. All right, I'll just leave it at that. So in this particular case, we use a type 2 LSA, also non-broadcast as well. For point-to-point, we do not use a LSA type 2. So there is no Drbdr election on point-to-point links, and that would apply also to the other point types. So the easy way to remember this for the exam, or in the case where you might have to be configuring this on the routers that are being established or establishing adjacencies over these point to any type of network, is there's no Drbdr election. So there's two aspects that we talk about. There are two aspects that we talk about when it comes to network types. One is there a Drbdr election? And if there is, how do we control that? And the other is there automatic neighbor discovery, or is there not automatic neighbor discovery? And when we go through our configurations later on, we will find out which topology types actually have a neighbor discovery and which topology types do not have a neighbor discovery. All right? Obviously, with a loopback, that's not going to apply in either case. Loopback interfaces don't have any peers. So Drbdr election is a moot point. Automatic neighbor discovery is a moot point because we don't have any adjacencies on those platforms. Okay? If you run into a situation where the network types are not compatible, you're going to end up with a situation where it might look like the nodes can actually form an adjacency, but when they do, their LSA flooding, they're not going to be able to solve the shortest path first tree, and they're not going to be able to route traffic to the prefix destinations. There is a specific place, and we'll see this later on, in the database where we have to look to see if the routing bit is set on the LSA, and if that bit is not set, it's going to mean that we could not install the route for our routing information base to allow us to use that route for processing. Okay? So let me pull up, well, I'm not going to get into the topology just yet. I was going to say, let me go ahead and pull up GNS3 and start to kind of go through some of these configurations. But before I do that, I'm going to maybe include a little bit more detail about each of these different network types. Draw a little sketch, and let me actually open up Paint here. So I can kind of visually show you what some of these networks look like. You know, typically in a LAN, we're usually dealing with Ethernet transports. So it does take, and by the way, this concept of Drbdr election, network types, and so on, that is a link state specific concept. So if you're used to using EIGRP, that's not something you normally would have to concern yourself with with the IGRP. So dynamic routing protocols, especially Ospf, you have to understand all the layer 2 topologies that Ospf works with, because Ospf is going to automatically treat those different topologies differently. So that's really the whole point of this discussion, is to educate you guys on the different network types, how they behave in Ospf, how do we handle these different network types with regard to establishing these adjacencies and so on. All right. There are essentially 3 classes of network types. That's going to show up in section. We'll pull up the RFC later, but I think it's section 1.2 of RFC 2328. Those 3 classes include point-to-point, broadcast, and non-broadcast. The 5th class is Loopback, which doesn't really it's not really defined as a network type specifically for purposes of routing. And the 6th class is a Cisco proprietary class, which is the point-to-multipoint non-broadcast. All right. So let's start with the point-to-point. It's actually one of the simplest types that you'll see in Ospf. You got router 1. It's got a single connection to router 2. Now that doesn't mean that connection is a point-to-point Ethernet connection. In fact, with point-to-point, we're dealing with protocols like HDLC, PPP, any kind of protocol that's essentially going to be considered a point-to-point type protocol. All right. Specifically with point-to-point, it could even be like a GRE tunnel, whatever it might be. So with this point-to-point circuit, I'll put GRE here as well. We send hellos as multicast, and we send them specifically to 224.0.0.5. All right. Like I said, there is no Drbdr Election. We only support, in this case, 2 nodes. See if I can type 2 nodes in this topology. All right, so if I go to my GNS3, let me go ahead and pull in a couple of routers here. I'll drop in, I'm going to use my iOS guys because I'm not, we don't have any serial interfaces on our iOS V guys. All right, so I'm just going to connect these guys using serial 20. And we'll go ahead and make this network 172.16.10.0/30. And this router will be .1. And this router over here will be .2. All right. We're going to kind of mix and match these configurations, if you will. We'll keep adding to this topology, and then eventually we'll get to the point where we kind of have everything together. So loopback 0 in this case, we'll go ahead and use 1.1.1.1/32 as our loopback on this guy, and we will configure a loopback on router 2 as 2.2.2.2/32. Those will essentially become my router IDs as well. All right, so we'll start our config, and I'm going to pause the video real quick so that we can just get our basic config in here, and then we'll come back. So we've got our basic configuration done on this point-to-point link between these 2 peers. I haven't configured Ospf yet, but we're going to be adding to this topology for the rest of the lesson today, really kind of taking a look at all of the different scenarios that you would run into with these different network types. That's why it kind of takes a little bit more time in this case, because we're actually looking at all of the different topology scenarios that we might see. All right, so I didn't do any Ospf in this particular case in this topology, so we're going to go ahead and add that. If I come into router 1, I'll just do a quick show IP route connected, so you can see we have, in this case, a loopback interface and a serial interface that's configured with IP addresses. So we're going to go and enable router OSPF1, our process ID on this router. As soon as I do that, if I do a show IP protocols, I can see that OSPF has started the process and we've elected our router ID for the process based on our loopback interface. Remember, that router ID selection process it's either manually configured. If it's not manually configured, we're going to go ahead and select the highest IP address on a loopback, and if we don't have any loopbacks, the highest IP address on a physical interface. So let's go ahead and go into interface loopback 0, IP OSPF1, we'll put that into area 0. Interface serial, we're going to do everything, I think. Well, we may not do everything in area 0 this time. We'll start with this side in area 0. Interface serial 20, IP OSPF1 area 0. So I've now enabled OSPF, show IP OSPF on those interfaces. And in fact, if I do a show IP OSPF interface, this is where you get to identify how OSPF has decided automatically what types of networks these interfaces are. So for example, the network type for a loopback interface, which is just a stub network, has automatically been detected as a loopback. All right. The cost of that interface we'll talk a bit later on about, and we can see that area 0 is attached to that network, but we don't really see any. Sorry, this guy here. We don't see any relation to timers. There's no hello and dead timers, so we're actually not sending hello packets over this interface because OSPF has automatically considered that this interface is a loopback. Okay, so it says, you know what, there's no way for me to form an adjacency with a peer on this interface. It's not a real interface, so we automatically treat this as a stub host. We'll talk about that a little bit more later on. For the serial 20 interface, if I do a show IP, show interface serial 20, pipe include protocol, you can see that, sorry, encapsulation. Is it encap? Yeah, there we go. Encapsulation on the interface is HDLC, which is one of those point-to-point protocols. All right? And OSPF recognizes that. It looks at the transport layer and it says, not the transport layer, but the data link layer, and it says, what type of transport am I using for the data link layer? And then based on that transport type, it makes a decision as to what network type it is. And because it's HDLC, it says, okay, the network type is point-to-point. Now, this is a really important concept because it identifies that the state is point-to-point. We're going to see later on where we have a state of broadcast or a state of waiting. We'll see that in a little bit. But most importantly, on our point-to-point, the hello and dead timer intervals are our default network intervals that we would typically see with a broadcast network. So we want to make sure we take a note of that the hello and dead intervals are 10 and 40 seconds respectively, because it will change depending on the network type. All right, so let me go ahead and configure the other router as well. Router OSPF1, interface loopback 0, IP OSPF1 area 0, and interface serial 20 IP. Actually, let me do this. Let's do a debug IP OSPF hello packets and hello, and let's do adjacency, and let's do events. We're going to kind of get all these things. And now let's turn on OSPF on that interface. IP OSPF 1 area 0. All right. So what I'm trying to show you here, what I want to show you here is obviously we're going to form an adjacency on that link because we've enabled OSPF on that interface. All right, let's take that off. So we see that the interface is going up, and as soon as that interface goes up, we're going to send a hello using 224.0.0.5. All right, and notice that I receive a a hello on that interface from router 1. But what you don't see in this process, which is what we're going to see later on when we start to get into our broadcast and multipoint networks, is you don't see a Drbdr election. Okay? We see a movement from the two-way state, which is obviously where the routers have decided that they can become peers, to sending our database descriptor packets, where we identify things, different flags and whatnot. We'll get into that maybe in another lesson in more detail. To receiving the DVDs, doing a master-slave negotiation on the interface to decide who's going to lead the conversation in the synchronization process. Master-slave does not have anything to do with Drbdr election. It's simply a way for us to identify who is going to do the database negotiation. We became the master in this case because we have a higher router ID. All right, but again, this is not a Drbdr election. So I send my neighbor my database descriptor packet. I receive a link state request from the peer saying, you know what? You sent me your database descriptor packet. I don't have this route. Can you send me that route? I send the link state update to that peer, which tells that router, hey, here's, and by the way, that's my loopback. And then we move into this exchange state. Once we're done with the exchange state, I send a link state request to my peer. I receive a link state update. I'm fully synchronized, and that's when we move into the full state. All right? So this is really one of the simplest types of networks that you can deal with, where you basically just have this point-to-point link running, we'll just say in this case, HDLC, and the routers do automatic neighbor discovery. They do not do a Drbdr election. The hello and dead timers are 10 seconds and 40 seconds respectively by default. And we just go through the normal adjacency state machine to establish the adjacencies between the peer. So let's make sure we got all the information here. We don't use Lsa Type 2 because it's not a broadcast network. There is no Drbdr election. I'll put an etc. here because there are some other network types that will manifest themselves as point-to-point. Frame relay, for example, would be one, but I'll put a little asterisk there, okay? Because not by default is frame relay going to be recognized as point-to-point, even though you might be configuring frame relay on a point-to-point sub-interface. We're going to send our hellos as multicast. We saw that in the debug. And we support only 2 nodes. The other thing I want to add here is automatic neighbor discovery. Automatic neighbor discovery takes place, meaning that we don't have to use a unicast or a static neighbor statement in our OSPF process to establish the adjacency and change our OSPF packets from multicast to unicast. All right. So far, so good. So let's go and take a look at our topology. And let's go ahead and establish, in this case, another couple of routers here. Actually, I'm not really going to do, I think we're okay on the concept of Drbdr. I'm going to go through a couple more things as part of this process. But we're now going to establish router 3 as a peer router to router 2, but using a LAN as opposed to a WAN, so that we can then go into discovering the next network type, which is broadcast. Okay? That's weird that that's green and the other one is not. Let me make sure I put it in the right interfaces. Ethernet 1.0 to Ethernet 1.0. Okay. Well, this router's not powered on. I guess that makes sense. So let's go ahead and make this network now a LAN, 172.16.20.0/24. In this case, and router 2 is going to be .2 in that topology, kind of following our .2 addresses on the .2 router. And we'll go ahead and make this router .3 in the topology, since this is router 3. All right, and actually I'll just make this network 2.3. All right, So we have subnetwork 2 to 3. This maybe should have been 1 to 2 or 12, but whatever. That's okay. All right, so we'll go ahead and power on this device and go into router 2 and set up the IP address on that interface. Interface Ethernet 1.0, IP address 172.16.23.2, 255.255.255.0, no shut. And let's go into router 3. Config T. Interface loopback 0, IP address 3.3.3.3, 255.255.255.255. Interface Ethernet 1.0, IP address 172.16.23.3. No shut. Okay. Router Ospf 1. So I'm going to start the routing process. Now, before we actually get into starting the routing process, I want to actually do a couple things here. So 3.3.3.3 is the loopback, which we know is also going to end up becoming the router ID for that router. Now that we've started the Ospf process, that's the case. All right, and we'll go to interface loopback 0, IP, Ospf 1, area 0, and interface Ethernet 1.0, same thing. So before I do that, we're already running a debug on router 2. Nope, I took them off. Let me turn them back on. Hello, adjacency, events. Okay. I'm going to do the same thing on here. Do debug. Let's just do this. Debug IP Ospf hello. We don't have debug IP Ospf like we do with the IGRP. Adjacency events, so we have to kind of do them individually. So now I'm going to go into interface Ethernet 1.0, and I'm going to run the command IP Ospf 1 area 0. And obviously in this case now I should start to see that Ospf is going to start communicating over that particular link. I sent a hello. I haven't received one because I got to do it on the other side here. Interface Ethernet 1.0 IP Ospf 1 area 0. So I should start to see quite a bit of information being passed back and forth between these peers. Sending a hello out of serial, sending hello out of Ethernet. There we go. Received a hello. Let's go back to router 3. So I'm sending hello, received a hello. All right, let's wait till we get into our full state. Once we get into our full state, we'll go back and look at these debugs. Received a hello, transmitting the DBD. All right. This would be, of course, much faster if we were running gigabit Ethernet interfaces. Ospf is considering this to be kind of a half duplex interface. So we would see maybe this occur a little bit quicker otherwise. Do undebug all. Undebug all. All right, so now let's take a look. We know that this is a multi-access network. Now when it comes to multi-access networks, let me go ahead and describe what a multi-access network is. Typically what we would describe normally as simply a broadcast network. It could be something like Ethernet, token ring, FDDI, but realistically, with most modern technologies today, we're simply dealing with Ethernet. In the case of a multi-access network, we do use Lsa Type 2 to disseminate information. So we are going to be sending hellos and updates as multicast in this particular case, but in the broadcast network or multi-access network, what we're defining essentially as Ospf network type broadcast, let's make sure we have, there's a Drbdr Election, and we're actually sending hellos and receiving hellos to 224.0.0.5 and 224.0.0.6 in this case. Okay, So broadcast would be essentially Ethernet, of course, FDDI, token ring, or any, potentially, I should say, any quote-unquote multi-access network. That would be hosts that share a common broadcast domain. So this could be, for example, frame relay point to multipoint, where I have or a DMVPN type network where I have a DMVPN hub that's talking to a bunch of DMVPN spokes. They all share a common broadcast domain on their tunnel interfaces, so that's going to be considered a broadcast domain. We do a Drbdr election. We already got that there. There is a Drbdr election in this particular case. So you do have to be particularly careful as to who becomes the DR in special topologies. This is definitely going to have implications on the topology design, right? For example, in a DMVPN hub and spoke environment, we need to make sure that the DR is placed on the hub. All right? So we support multiple nodes in a common subnet in this topology. All right. We also see that there is automatic neighbor discovery in this case. And if we go back to our router, well, before I do that, let's go ahead and take a look at these debugs. So I went ahead and I enabled Ospf on the interface. And I meant to show you this in the debug in the show outputs, but I'll shut down the interface and we'll go through the adjacency process again so I can show you this. The interface goes up. I send a hello to 224.0.0.5, basically just letting everybody know, hey, I'm here. And then you can see sending another hello, sending another hello. That's when I hadn't enabled it on the other interface at that point. Finally, I enabled it on the other router, and I received a hello. Okay. I send an immediate hello to that neighbor, and essentially what we're doing in this particular case is we're comparing our properties, the properties of our peers, to identify whether or not we're compatible, whether we can become neighbors and form a full adjacency. So we're sending and receiving these hellos, and that's when we move into a two-way state. The two-way state, if you recall, indicates that, hey, I'm in your neighbor list, you're in my neighbor list, and we've established that we can actually move beyond the two-way state and continue through the Ospf adjacency state machine to identify that we become full neighbors. All right? So you'll notice here this line right here, and this is what I wanted to show you. I'll show you again after this, but there is a predetermined wait time in Ospf before we decide what role we're going to play in that topology. All right? I'm going to talk about that again in a minute here. I don't automatically just assume that the router 1, router 2 in this case, was the only peer that I could establish an adjacency with. And I'm trying to decide as I come up and I start to operate in the topology, what role I'm going to play in this multi-access network. And this is where the Drbdr election takes place. As we talked about in one of our previous lessons, the Drbdr election is based on the priority of the interface, number 1, which is by default a priority of 1. And I will kind of put this in the notes as we, actually, let me do that now. Okay. When there is a Drbdr election, we must consider the following. Number 1, the router with the highest interface priority in the broadcast domain will have priority to become the DR. Okay? Now, that being said, priority values are 0 to 255 and highest wins. With 0 meaning you can never be elected. This is what we talked about in our last lesson. The default priority on all OSPF interfaces is 1. And this is configured on a per interface basis. All right? So there has to be a tiebreaker. And that tiebreaker is the router ID. Highest wins. All right? However, this process is non-preemptive. And some people might define it as non-preemptive. Some people might define it as preemptive. Certainly a router can preempt the role if it thinks it's lost connectivity to the DR. So if I'm a BDR and I believe that I've lost connectivity to the DR, there's nothing that says that, in fact, it's by design, I would go ahead and preempt that role and take over the role as the DR. Okay? But as long as I notice that the DR is active, and there's a keep alive mechanism that takes place, and it's part of the hello packets and whatnot, as long as I can identify that the DR is active, then I'm not going to take over the role as the DR in this particular case. So going back to our topology diagram here, for multi-access networks, what we would consider to be broadcast, we essentially would have, in this case, multiple routers that are connected to this segment, which is just a regular LAN segment. And each of those routers are going to have a priority configured on their interfaces. Let's say it's the default priority of 1. And they're each going to have their own router IDs. As we do in our topology. All right? That's supposed to be a 4. So if I was just to base this election process solely on the rules, lowest or highest priority wins. After the highest priority, then we have the highest router ID. Then logically it makes sense that router 4 would become the DR in this particular topology. And router 3 would become the BDR. And most importantly, these routers all form a full adjacency with the DR. The relationship that we have between these two routers is going to be two-way. There is no full adjacency between those two routers. They recognize each other as potential peers. They do recognize each other as neighbors, but they're not going to be exchanging link state information. And that's really the whole point. So if something happens on, say, this router here, a link goes down or whatever, I'm going to go ahead and notify the DR, and then the DR is going to propagate that information to the remaining routers in the topology. And this is something we talked about in the last lesson. It's what we consider a multi-access network. All right. And that multi-access network needs to be managed. All right. So the whole purpose of this election process is to reduce the overhead in the segment and then make OSPF a little bit more efficient. All right. Now we do have other network types that we need to talk about. For example, non-broadcast. So before we get into that, let's take a look at some of the other components here. Actually, let me go back to my router here, my notes, excuse me. And let's see, do we have everything we need for multi-access? Oh, we're up here. Okay. Broadcast, automatic neighbor discovery. The timers. We need to verify the timers for the interface. Oh, and by the way, I totally forgot to mention, after this wait period, which we're going to go ahead and take a look at in a minute, we do our Drbdr election. I've promoted myself as the BDR because I've ended the wait process and nobody else on that segment has identified themselves as the DR. So I automatically put myself in the role of the BDR, and then after I don't see any indication that another router is the DR, I will promote myself to the DR. Remember, I didn't start the Ospf process on router 2 until after I started it on router 3. So the router 2 becomes the BDR, and that's how we identify those. And then we move through the rest of our process of forming our full adjacency. Okay, DBD negotiation, send DBDs, link state request, link state update, exchange done. Then we go in the other direction, link state request, link state update, and then we move into the full state. Now, if I do a show IP OSPF interface Ethernet 1.0, you can see that this network type has been discovered as broadcast. We will identify, in this case, the designated router and the backup designated router on that link. And then also we see, the neighbor counts and whatnot, and the idea, which neighbor is performing what role in the multi-access network, but more importantly, hello and dead timers. Okay, so let's put that in our notes. Our hello and dead timers are the same as our point-to-point timers in our point-to-point network type. All right? So that begs the question then, if I configure one side of the network as point-to-point and the other side of the network as broadcast, will that affect the adjacency process? Will the router still be able to form an adjacency? And essentially what's going to happen in that scenario? So let's go ahead and take a look at that. So I'm going to go into my topology here. I'll fix it after we're done kind of doing the discovery here. I'm going to configure router 3's interface as a point-to-point interface as opposed to broadcast. So I'm going to go into interface Ethernet 1.0, IP, OSPF network type, point-to-point. All right, and I'll even clear, excuse me. Let me go ahead and actually do our debugs. Do a debug, IP OSPF adjacency, events, and hellos. And I'm going to do a clear IP OSPF process. And let's see what we see in the adjacency process. So we're moving, we're actually rather quickly through the adjacency process to a full state. So let's do an undebug all. And if I look from the process from the beginning, undebug all, there we go. Look from the process at the beginning, loopback interface, down, down, we cleared the process. Obviously we're resetting the interfaces. Neighbor relationships go from full to down. And then we start to bring everything up. I send a hello using multicast, so that's actually a good thing because broadcast networks also use the same multicast address. I receive a hello and I form a two-way adjacency. So this is the example where I said, or when I talked about this in the beginning, is the routers can still form an adjacency, or at least they can identify each other as neighbors even if they're not running the same network type. All right? Now the question is that going to affect the resolution of our domain? Right? Just because I can become adjacent with a peer doesn't mean that I'm actually going to be able to route to that peer. All right? So sending a DBD, receiving a hello, etc., negotiating, it looks like we're going through the process. link state request, link state update, and then we go from loading to full. All right, so if I do a show IP OSPF neighbor, I can see that I do actually have a full adjacency with the peer, although from this router's perspective, no Drbdr election, which makes sense because there is no Drbdr election on point-to-point links. If I go to router 2 and do the same thing, show IP OSPF neighbor, for router 3, I actually see or assume a priority of number 1, and I'm doing a full adjacency, and it's identified that peer as a BDR, which is actually kind of strange because how could I possibly identify the peer? First of all, the priority, if the router's not sending a priority because it's point-to-point, how could I identify that priority, and how could I identify that router as a BDR? All right, let's see show IP OSPF database. 3.3.3.3. Let's look at the router ones and see if there's a problem. And sure enough, the advertising router is not reachable in the topology, which means that even though I was able to form an adjacency, and even though it looked as if we were able to exchange routes, we are not able to resolve the topology, which means that the 3.3.3.3 address, show IP Ceph 3.3.3.3 has no route. Okay, so I can't ping 3.3.3.3. I'm not receiving. I'm receiving an update about that network. So there's the address, there's the mask, there's even the metric, and I'm getting that from router 3, but I can't route to it because it's not resolvable in the topology because of the mismatched network types. This could be a really, really frustrating problem to see because on the test, you might be going through your standard process. Oh, do I have a neighbor relationship? Maybe you're doing it quickly, you're not looking, you don't realize that, that there might be a mismatch between the network types. So you see the neighbor, okay, I've got a neighbor. You look at the database, oh, I'm getting routes, or I'm getting type 1 LSAs from that peer, but there's no reachability to router 2 as the DR from router 1 because router 1 doesn't understand what type 2 LSAs are. Router 2 is sending out type 2 LSAs. Router 1 is ignoring them because it's a point-to-point router, so it's unable to resolve the topology. Okay? So even though we were able to kind of get through most of the process, it doesn't really work that way. So let's do IP OSPF network, and neighbor will reset, and we'll go down and come back up. All right? All right. Next step. Let's talk about the other network types, and we're going to take a look at some configurations of the other network types and see what some of the differences are between those as well. In that multi-access network, like I said, the DR is kind of acting as a route reflector, if you will, but it's not modifying the next hop value. In other words, it's not advertising itself as the next hop for those prefixes that it's advertising. Just basically passing the updates on. The BDR itself, I forgot to mention this, in that multi-access topology is not used for calculating or flooding. It's just waiting for the DR to die, essentially. And then we talked about the concept, how the other routers are druthers in this particular case. And those routers will stop in a two-way state. All right? So we talked about priority. If I wanted to change the priority, okay, I could certainly do that. For example, go to router 2 here and config T, interface Ethernet 1.0, IP OSPF priority, and I can set that priority to whatever value I want. All right. You'll notice actually that priority value, show IP OSPF neighbor, is actually learned relatively quickly. There we go. Because it's sent within the hello packets. So you'll see here I got down to my 30 seconds, which means that I hit my 10-second update timer. So I went back up to 40 seconds, but in that hello packet I was able to identify the priority. Router 2 was already the DR in this case, so changing the priority didn't affect anything. But if router 3 would have been the DR, it still wouldn't have changed anything in the topology because the election is non-preemptive. So even though router 2 is now advertising a higher priority, it will not be elected as the DR. That's what's strange about this process is even though you have these mechanisms to control the election process, there's really no way to truly control it because it would mean that you would have to identify exactly how the routers are booting up, what steps they're going through to boot up, because once a router claims the role of the DR, it's not going to lose that role even if somebody comes along better with a better value. Okay? All right, let's see here. Let's go ahead and set up a point-to-multipoint circuit. And in order to do this, we are going to have to set up some frame relay. So let me pause the recording. So what we got here is we've got a frame relay network, which is, well, we'll get into that in a second. We've got a frame relay network. Oh, Mike, you had a question here. Let me see. Can you do a priority of 255, 254, and zeros on all the others? Yes. As long as you have a DR, BDR in your topology. In fact, you really don't even need a BDR. As long as you have a DR, you can still form adjacencies with all the other routers, and we can still converge the network. However, if the DR fails, then you're not going to have any kind of backup. Conversely, if you made a DR 255 and a BDR 254, it's really no different than doing 2 and 1 or whatever. The higher the number does not add any more importance to the election process. But if you don't have a tertiary router that has some sort of priority set, if the DR fails, the BDR is going to get promoted to the DR, and then you're not going to be able to select the DR. Another BDR. So you would have to have 2 failures in that scenario in order for the network to stop functioning. But that's highly unlikely in a lot of topologies with modern technology today. We're probably not going to see two devices failing on the same multi-access network. So you may want to just ensure that you have 2 routers that perform that role. And you can absolutely do that. So what we're going to do is we're going to look at the configuration here. And the first option we're going to take a look at is what we call point-to-multipoint. Multipoint frame relay. Okay? Where essentially everybody in this topology shares a common broadcast domain. That broadcast domain is 30.0, and each of these clients are then reachable within that subnet based on the IP address on their interface. So let me go into router number 4 and go into the console port here. And I got to do my basic IP configurations first. If it's going to load up here. There we go. Config T. Config T. Get there eventually. Interface loopback 0, IP address 4.4.4.4, 255. By the way, frame relay is probably not going to be covered on the exam. This would be a very similar situation to where we're doing DMVPN, except for in DMVPN, the network type is automatically discovered most likely as broadcast, not non-broadcast. Interface serial 20, IP address 172.16.30.4, 255.255.255.0. Now I'm going to do encapsulation frame relay on this case. All right, and that's it. I'm just going to run frame relay encapsulation. We're going to use LMI and other mechanisms within frame relay to automatically discover the frame relay network and what delcies are mapped to what. We'll use inverse ARP to identify the peer that's on the other side. We'll do no shut. And before I enable Ospf, I'm going to go ahead and leave it at that. Let's go into router 5. All right, we'll do the same thing, config T. I just cannot type that today. Interface loopback 0, IP address 5.5.5.5, 255, 255, 255, 255. Interface serial 20, IP address 172.16, .30.5, 255, 255, 255.0, no shut, encapsulation, frame relay. All right. And then finally, we'll do our hub router. This is a traditional hub and spoke topology that we're dealing with here. And router 3 is acting as the hub in this particular case. If this was EIGRP, we would have to do things like disabling split horizon, those kinds of things. Actually, let me close that tab. I already had it open here. So config T, interface serial 20, no shut. All right. IP address 172.16.30.3, 255, 255, 255.0, encapsulation, frame relay. All right. Now, remember, frame relay is a layer 2 transport. It is not reliant on layer 3. So we can go ahead and verify the functionality of our peers, at least reachability over the network, before we even start to take a look at network types and OSPF and applying OSPF. So we can do a couple of things here to verify. If I do a show frame relay map, I can identify whether or not we're actually establishing some sort of frame relay connectivity with the other routers in the network. All right, so it looks like the network state went to down. Let me make sure. Show run interface serial 20. That should be all we need. Show frame relay PVC and map. So we're not getting, there we go. It is kind of slow in the case of frame relay. So it's going through the whole process of discovering the frame relay LMI type, going through the inverse ARP process to identify who's on the other side of the link. So if I do a show frame relay map now, I should see, show frame relay PVC. Interesting. Show frame relay. LMI. Okay, we're running ANSI. DTE, LMI type is ANSI. That's fine. Should work in GNS3. Show frame relay map. There we go. So it just takes a little bit of time. So frame relay is an automatic protocol at layer 2, and it goes through this whole process of ARPing, inverse ARPing the destinations and so on. So you have to kind of be patient with that. But what is this telling me? It's telling me that on my serial 20 interface, I recognize that there are two PVCs, two virtual circuits. There's a Delc 300 and then there's a Delc 301. Remember, these Delcs are layer 2 addresses. They're not layer 3 addresses. They simply identify the entrance of the tunnel to the frame relay provider. So as this router is encapsulating data and it's sending it over to the frame relay switch, it's encapsulating it with a stamp of the particular Delc on that interface. Okay? In this case, then the service provider is going to look at those encapsulations. Let me see if I can show you what those look like. Start a capture here. So instead of an Ethernet header, we have a frame relay header, and inside of that frame relay header, we're essentially, quote unquote, tagging the frames, even though it's not referred to that in frame relay, with the Delc so that the frame relay switch knows which PVC to send that traffic over. So I should see in this case, I might have to generate some traffic, but I should see in this case that we are generating frames, frame relay frames that include some sort of Delc indicator. Okay? Not that that's related to OSPF by any means. It's certainly not. But when we enable OSPF on this frame relay network, some interesting things are going to happen and it's not going to work. All right? So we're waiting for this to come up here. Choo-choo. All right. So, remind me later. That is, source destination. Yeah, that's okay. I'm trying to see if I'm seeing any of my frame relay frames. Let's filter out That's really strange. Wireshark's not really liking these frame types. Let me generate some traffic. May not be able to see this here, but let me ping 172.16.30.4 and see if I see that data. There we go. All right, so let's go ahead and open up this payload here. Interesting that it's recognizing it as HDLC, even though technically it should be frame relay. Let me check something on the router here. Show interface serial 20 pipe include encap. Yeah, it's weird. So it's actually showing up in Wireshark as an HDLC frame, even though it's a frame relay frame. It's not really that important. I'm not sure why Wireshark is doing that in this particular case. Certainly the encapsulation should be frame relay. Maybe it's that Wireshark doesn't support that. I'd have to do a little bit more research on that. But in any event, we're sending frame relay data. So now I'm going to go ahead and enable Ospf on this interface. Config T interface serial 20. And I'm just going to say IP Ospf1 area 0. All right, and I'm going to do the same thing on the other routers here. Config T interface loopback 0. No interface loopback 09. Interface loopback 0 IP. Actually, we got to enable Ospf first. Router Ospf1. Interface loopback 0 IP Ospf1 area 0. Interface serial 20 IP Ospf1 area 0. And then we'll do the same thing on router 5. Config T. Router Ospf1. Interface loopback 0 IP Ospf1 area 0. Interface serial 20 IP Ospf1 area 0. All right. So I've now enabled Ospf on serial 20 on all these interfaces. Now I should see adjacencies, right? If I do a show IP Ospf neighbor, I don't see any adjacencies with router 4 and router 5, which brings us to our non-broadcast election. We're doing a Drbdr election, but because it is non-broadcast, automatic neighbor discovery is not done. Non-broadcast means no multicast, which means that the router, in fact, if I go into my router here and I do a show IP Ospf interface serial 20, show IP Ospf interface serial 20, you can see that it has automatically identified, based on the encapsulation on the interface, that frame relay is a non-broadcast network. And we can see that we're kind of stuck in this waiting state. We're trying to, that means there's a Drbdr election, by the way. We're stuck in this waiting state. Notice the timers are different as well. For any kind of NBMA network, the timers are 30 seconds and 120 seconds. So now we're starting to see in this, with this network type, there's quite a few differences in the topology and how Ospf interprets the topology. So let's say that I want to fix this, okay? First of all, because it's non-broadcast, that means no automatic neighbor discovery, but we are going to do a Drbdr election. In the case of a point-to-multipoint type design like this, we want this router to become the DR. We don't want the spoke routers to become the DR because they don't have direct connectivity to the other spoke routers. So the first thing that I'm going to do in this case is I'm going to go into the Ospf process, and I'm going to say, actually the interface, excuse me, interface serial 20, and I'm going to say IP Ospf priority 0. So I do not want this router to become elected. There's another way that we can do this. I'll explain how we can do this on the hub. but this is typically how we would do it. Go into serial 20, IP OSPF priority 0. Okay? So that would fix at least the situation where we have to have a specific router acting as the DR. The next step, though, is that because there's no automatic neighbor discovery, we have to statically define our neighbors. So I'm going to go into my OSPF process. Actually, let me go to my notes first. No automatic neighbor discovery. You must statically define the neighbors. And also this is typically, I forgot to mention this, I'm trying to kind of keep this in order here. This is typically going to be like frame relay, ATM, X.25, etc. These are the kind of networks that are going to be running, that are going to be identified as non-broadcast automatically by OSPF. So I've got different hello and dead intervals. That's going to potentially cause a problem. Automatic neighbor discovery is not allowed. We will have to statically define our neighbors, and that's using the neighbor command. In the routing process, we use the neighbor command. All right. Now here's another interesting concept of that. I'm in the process. I'm going to go ahead and use neighbor 172.16.30.4, and then I can specify, if I want to, the cost of the link for that neighbor. Why would this be particularly important with frame relay? Because the cost is the bandwidth, and the bandwidth is normally based on the physical speed of the interface, versus in frame relay, bandwidth is typically based on something called the committed information rate of the PVC, the virtual circuit that connects the two peers. So you could specify the cost, but I'm going to go ahead and say, let's go ahead and give that neighbor a priority of 0. And I'll do the same thing for router 5. And as soon as this occurs, we start sending out our hello packets using unicast. So hello packets, we send hellos as unicast packets based on the static neighbor discovery configuration. All right, so you can see as soon as I define those neighbors, I got my adjacencies between those peers. Which is interesting because I didn't define the neighbors on the other side of the link. Well, OSPF is designed to respond to a hello packet. So router 4 and router 5 received a hello packet from router 3. They know that they need to respond, so they're going to send their own unicast hello because they know where the hello packet originated from, and then we can form our adjacency. So if I do a show IP OSPF neighbor, we can see that for router 4 and router 5, the priorities are 0. It is trying to do a Drbdr election. So because it's a multipoint topology, non-broadcast multipoint topology, we've identified router 4 and router 5 as DR others because they can never be elected because the priority we set for those peers is a priority of 0. I technically would not have had to go in here and set the priority to 0 on the interface because based on router 3's configuration, when we identified the peers, we said this peer can only have a priority of 0, which means we're never going to try and look to that router to become the DR or the BDR. Honestly, in this type of scenario, I would say it's better to kind of statically configure that on the interface as well. So we've got our full adjacency. If I come in here and I do a show IP OSPF database router 4.4.4.4, I can see that I am getting my router link states. I don't have any issues with those link states not being usable. So we are able to resolve the tree and identify which node that we're going to go to. And if I ping 4.4.4.4, it pings through just fine. Okay, so let's just summarize here. Did we miss anything? Non-broadcast, it assumes that it's a multipoint. So assumes it's multipoint. which, by the way, frame relay. Sorry, I had a sneeze there. Frame relay is not always multi-point. Frame relay can be deployed in terms of point-to-point as well. There is a Drbdr election. These are the types of technologies that will be identified. Automatic neighbor discovery is not done. We have to statically define the neighbors. Hello and dead timers are 120. Okay. Frankly, we don't ever really try to use this network type anymore. And here's the reason why. If I go to my frame relay maps, show frame relay map, I can see in this case that broadcasting is actually supported over this frame relay network. That used to be something that the service provider would control. And a lot of times service providers would not allow broadcasting over the frame relay network because it would saturate the network and it would affect all their customers within the domain. It's not that frame relay doesn't support broadcasting. It is entirely possible to send broadcasts and multicast over a frame relay network as long as the PVCs are established to do so. And in our particular case, they are. But I don't really like this network type. Now, I could do something like this. I could go into, config T, interface serial 20, and I could see IP Ospf network point to multipoint. All right. In fact, let's go ahead and do a show run pipe section router. And let's take out our neighbor statements. All right. And we'll get rid of 4 as well. All right. And I've changed my network type. Now, if I do a show interface, show IP Ospf interface serial 20, you will notice in this particular case, as a point to multipoint interface, all right, there is no Drbdr election because we would see a reference to that here, and the hello and dead timers are still 30 and 120. So let me go back to my notes. I've now changed this interface type to point to multipoint. No Drbdr election. The hello and dead timers are 30 and 40 seconds respectively. Because it is not a non-broadcast network, automatic neighbor discovery, let's see, automatic neighbor discovery, I want to use the same verbiage here. Well, that's it. Automatic neighbor discovery is permitted. And if we look at our topology, go back to the database here, the router, show IP Ospf neighbor, we can see that 4 and 5 are in fact still neighbors. But if I do a show IP Ospf database, router 4.4.4.4, we see again that we're running into problems. We're not having a problem with adjacencies, but we're running into problems with resolving the topology. Because again, it's kind of like that whole broadcast versus point-to-point. The network types are not really compatible with each other. Non-broadcast is trying to do things differently within Ospf than this point-to-multipoint. So I could, in this case, come to router 4, interface serial 20, and I could say IP Ospf network point to point, config T, interface serial 20, IP Ospf network point to point. All right. Now, let's see if we have our adjacencies in this case. Show IP Ospf neighbor, 32, 31, 30, 29, 28. Uh-oh. We've gone below the 30-second threshold here. Oh, that's right. Our timers have changed, right? We're sending these hellos every 30 seconds. So show IP Ospf database router 4.4.4.4 still have an issue. The advertising router is not reachable within the topology or within the tree. So let's take a look. Do show IP Ospf interface serial 20. And we do see it's point to point, but here's the problem. Hello and dead timers on point to point is different than the hello and dead timers on point to multipoint. Right? We saw that already from this configuration. So even though they have similar configurations, do not use an LSA Type 2. There is no Drbdr Election. Automatic neighbor discovery is supported. Move this up, kind of making them the same here. Automatic neighbor discovery is supported, but we don't have the same timers, which means that we're not going to be able to form an adjacency, because even though we recognize one another, one of the fundamental elements that need to match in order for routers to form an adjacency is their hello and dead timer. So I could, in this case, go to router 3, for example, and simply change the timer. Interface serial 20, IP Ospf, hello interval, and I'm going to change that to 10 seconds. Automatically, it's going to change the dead timer to 40 seconds, and we should see our adjacencies come up. Let me do show IP Ospf interface serial 20. It is still point to multipoint, but now we have a 10 and 40, and sure enough, we see our adjacencies come up. So on the test, they may ask you to fix a problem a certain way. And it could be, you can only fix this problem by adjusting timers, or you can only fix this problem by adding some configs, but you can't take away config. You see what I'm saying? So definitely something to consider. Now, one other aspect of this configuration that I want to look at. Let's make sure I think we've got our point to multipoint. Point to multipoint is going to be similar, right? It's going to be the similar topologies that we're going to see. Let's see, no Drbdr Election, so that will go after that. And because there is no Drbdr Election, we're going to send hellos. Automatic neighbor discovery is allowed in point to multipoint, so we're going to send hello packets using multicast, and so on. All right. Loopback, that's pretty simple. We don't really need to talk too much about that. We simply advertise networks by default as host routes. So /32, even if they aren't. And we can change the network type to allow the configured prefix to be advertised, which is not something we would typically do anyway. These are stub networks. You know, there's really no reason to advertise a prefix. You might see it in a class somewhere where they're just trying to generate additional subnets or whatever, and that's what they're doing in that particular case. Okay. Let's take a look at one more thing, and then we'll wrap up our session for today. Let me save this before we move on. Save as. And let's go to Google Drive, class shares, CCIE, routing topics, and Ospf network types. All right, and that's based on this topology that we have here. I want to maybe do something a little bit differently. So rather than have, let's go ahead and stop our capture here. Rather than have this set up as a non-broadcast multi-access network, I want to segment out router 3 to router 4 and router 3 to router 5 into two different subnets. We're going to go ahead and leave this guy. We'll call this network 34, and it's going to be a /30. And we're going to configure .3 on that subnetwork for that PVC, and this guy will be .5. Actually, let's make this a .29, so that'll work. And then on the top side, we'll duplicate this. We're going to go ahead and set this as 34. Excuse me. This is going to be 35. router 3 to 5 and router 3 to 4. And this guy will be .3 for that subnet, and this guy will be .4 for that subnet. All right, so let me go into router 4 and change this configuration. Interface serial 20, IP address 172.16.34.4, 255.255.255, /29, that'll be a 248, okay? And then I'm gonna go to router 5, config T, interface serial 20, IP address 172.16.35.5, 255.255.255.248. You'll notice that we lose our interface, we lose our adjacency, obviously. But now what I have to do in router 3 is something a little bit different here. Okay? Let's do a show run interface serial 20. And we're going to go into interface serial 20. We're going to do no IP address and no encapsulation. Let's also take off IP Ospf network and no IP Ospf hello. And actually, let's even take off OSPF altogether. I guess I could have just defaulted the interface, but area 0. Okay, no IP Ospf. So do show run interface serial 20. All right, basic config, actually blank config on that interface. So when you're setting up frame relay, and in this case we're actually going to be creating a, in this topology, we're going to do a point-to-point frame relay deployment. All right, and we could do this as multipoint if I wanted to do this as multipoint, but essentially I'm separating these PVCs into their own separate broadcast domains and treating them like their own separate subnets. This is a traditional hub and spoke deployment. So what I would have to do is go into my router, and I'd have to go interface serial 2/0, and I would have to create a sub-interface. We'll call it for router 4.4. Actually, let me go into the main interface first. In order for me to do that, I have to do encapsulation frame relay on the primary interface. Now I can go into interface serial 2/0.4, and you'll notice that, why isn't it letting me do that? Interface serial 20.4, there we go. I guess I had to go back one step. So you notice here I have an option of establishing this sub-interface as a multi-point sub-interface or as a point-to-point sub-interface. OSPF is going to recognize this. We're going to do a point-to-point, and then we're going to do a frame relay interface delc. We're going to send 300 or tie delc 300 to this interface, give it an IP address, why isn't it letting me assign an address? Oh, no, that should be it. 0.4, exit. I keep doing that. IP address, I'm trying to use my tab completion when I'm not in the right mode. IP address 172.16.34.3, 255.255.255.248. And so what I've essentially done in this case is I've split the interface. Let me do the other sub-interface. Serial 20.5.2 and we're going to do frame relay interface delc 301 in this case. IP address 172.16.35.3, 255.255.255.248. So if I do a show run pipe begin serial 2/0, you will see in this configuration, I've got the encapsulation running on my primary interface, which enables frame relay. And then I've created two sub-interfaces, one that has Lsa 300 tied to it, which is then tied to that broadcast domain, and one that has Lsa 301 tied to it, which is in the broadcast domain 35. All right. So if I do a show IP OSPF interface serial 20.4, oh, yep, that would help. Let's do that. Config T interface serial 20.4 IP OSPF 1 area 0, and let's do 5. You can see we immediately formed our adjacency. All right, now if you recall, router 4 and router 5 do show IP OSPF interface serial 20. We had already configured this as a point-to-point link on this side, so it has the appropriate hello and dead timers. And because we created the sub-interfaces in this case as point-to-point, they already had the same configuration. I could have created them as multi-point interfaces if I had some other endpoints or spoke routers that were going to those interfaces. And in that case, I would have to modify the timers because point-to-multipoint uses a 30 and a 120 timer, not a 10 and 40 timer. So if I do a show IP OSPF interface serial 20.4, you can see that it's recognizing that interface as point-to-point, no Drbdr election, hello and dead timers, 10 and 40. Okay? Like I said, you guys are probably not going to have to deal with this when you're on the lab, certainly not frame relay, but these are some of the considerations that you would have to take into account if you're dealing with other modern technologies, particularly modern VPN technologies like DMVPN and so on. I do recommend that you take a brief look at RFC 2328, specifically sections 12.4, which talks about all the different network types, and section 9.4, which goes through the whole Drbdr election process and adjacency process. Is there anything else I want to show you for today, though? Let me see. Let's check our notes one more time. Make sure that we have our descriptions for all of these here. Point-to-multipoint non-broadcast is exactly the same as point-to-multipoint. There is no Drbdr election, and as with our non-broadcast, automatic neighbor discovery is not done. We send hello packets with unicast, or hello packets are sent in unicast, but you have to statically define the neighbors. All right? I know there's a lot of information. We had talked a little bit about this briefly when we were in our previous lesson, but hopefully this kind of made things a little bit more clear. It's a little bit challenging to keep in mind, to remember. But when you guys are in the lab on the exam, just remember, and this is really the most important concept, just remember that you always have to be cognizant of the OSPF network type. That is the most important aspect. Understand the OSPF network types, understand the implications of having different network types, how to verify those using show IP OSPF interface, how to go through the process of troubleshooting that, maybe changing some of the configurations, and understanding, most importantly, that just because you have an adjacency, two-way, or even a full adjacency does not mean that you have reachability. So don't assume that when you have a neighbor and you see information coming from that peer in your database that you actually have a full adjacency with that particular peer and that you're actually exchanging routable information. All right, let's see. I guess that's about it, unless you guys have any questions to wrap up our session today. Nope. Okay. I know I need to upload some of these. I will do that tonight. I absolutely promise. Let me go ahead and shut off this recording.